So we're going to do section 8, chapter 2, which is the last section that we're going to cover, in chapter 2. So like I said a few months ago, the test is going to be 1 week from the day. The test is going to be 1 week from the day. Remember, next Tuesday is assessment day, so we won't be meeting for class. I already have chapter 2's review attached to our homework section in Blackboard. Also keep in mind I'll be in the office this afternoon, as well as I'll probably just send an email saying what times I'll be in the office on Tuesday, because we want to meet just in case anybody has any questions. But today we're going to be going over function operations and the composition of functions. All right, so first, function operations. The first operation, we go over the operation of addition. We are asked to find f plus g. By definition, this is f of x plus g of x. We're asked to find f minus g. By definition, this is f of x minus g of x. We're asked to find fg, is understood to be multiplication. So by definition, this is f of x times g of x. And we're asked to find f divided by g. By definition, this is f of x divided by g of x. All right, so whenever we're talking about operations of functions, when they're going over the operations, they just mean addition, subtraction, multiplication, and division. This is with the given, understanding that we're given two functions, namely f of x and g of x. All right, so an example is that we're given the function f of x, which is x squared minus 3x, g of x, which is 4x plus 5. And we're asked to find all the operations of those two functions, as well as their domains. So we can start with f plus g, which by definition is f of x, or in this case, x squared minus 3x. Plus g of x, which is 4x plus 5. So all we're really doing is going through combining like terms because we're adding them. We don't have to worry about the parentheses. We can drop those off. And I'll go over when you need to really focus on putting in parentheses, because that's a very common mistake that I see. Here we only have two like terms, namely negative 3x and positive 4x. This means that x squared is going to be a part of my answer. Negative 3x plus 4x, or 4x minus 3x, leaves me with a positive x. And we don't have any like terms for positive 5. So f plus g of x is actually x squared plus x plus 5. The next operation that we need to find, f minus g, or f of x. Once again, that's x squared minus 3x, minus g of x, which is 4x plus 5. Note that this time, when I'm subtracting g of x, I did put it in parentheses. And whenever you're subtracting a quantity, I do suggest that you plug it in parentheses. Just for the simple fact, the most common mistake that I see is that people have a tendency to forget that it's an understood negative 1 in front of this parentheses. Or another way of wrapping your mind around that concept, we're subtracting every element in this form inside the parentheses here. So once again, we're basically combining like terms. Here, we have x squared that has no like term to combine it with, so that's going to be a part of my answer. We have negative 3x minus 4x. Negative 3x minus 4x, the signs are the same. So we should really be adding and keeping that sign. Negative 3x minus 4x is be a negative 7x. And we're actually subtracting a positive 5, which has no like term to combine it with. So that negative 5 is going to be a part of my answer. So f minus g is the polynomial x squared minus 7x minus 5. Next operation, f times g. Here we're going to have x squared minus 3x, or f of x. And this time it's being multiplied by g of x, which is 4x plus 5. So essentially, what we're doing is FOILing this out, or we're multiplying two binomials. So we can FOIL it out. We're gonna have x squared times 4x on my first two terms in each binomial. X squared times 4x gives me 4x cubed. My outside terms, x squared times a positive 5 gives me a positive 5x squared. My inside terms, negative 3x times positive 4 will give me a negative 12x. Oh, excuse me. Inside terms, negative 3x times positive 4x gives me a negative 12x squared. Then my last term, negative 3x times positive 5, be a negative 15x. All right, so foiling it, we have the polynomial 4x cubed minus 5x squared minus 12x minus 15x. We need to combine our like terms, of which we have two, positive 5x squared and negative 12x squared. So that 4x cubed is going to be a part of my answer, as well as that negative 15x. I'm going to go ahead and combine those like terms. Positive 5x and a negative 12x is going to give me a negative 7x squared. And we can bring down our negative 15x and be a part of my answer. So f times g gives me the polynomial 4x cubed minus 7x squared minus 15x. All right, so we've handled f plus, f minus, excuse me, f plus g, f minus g, and f times g. Last one is f divided by g. By definition, is just f of x divided by g of x. So we're going to have f of x, or x squared, minus 3x, divided by g of x, which is 4x plus 5. Now, here this is actually written in the simplest form. The only thing that we can actually do is try to factor it. In the numerator, we can factor out x from each of the two terms, but in the denominator, we don't have an x in each of those terms to factor out with it. So essentially, there is no canceling, there is no combining of like terms, there's no other operations. F divided by g of x is actually this rational function, x squared minus 3x, divided by 4x plus 5. All right. Now, in terms of the domains of these functions, note that f plus g is a polynomial, f minus g is a polynomial, and f times g is a polynomial, or it's a collection of terms. Remember, the domain for all polynomial functions is the entire number system. By interval notation, you can say the domain for all will be from negative infinity to infinity, or we can use any value of x and still get a real number as our solution. Now, this is true for f plus g, f minus g, and f times g. But for our rational function, f divided by g, remember, we can't divide by 0. So any x value that'll take our denominator, in this case, 4x plus 5, and make it equal to 0, we have to exclude in our domain. So for the rational function, or f divided by g of x, it's going to be the entire real number system except for our rational function, f divided by g, where x cannot equal a negative 5/4. Remember, we get that negative 5/4 by simply taking that denominator, setting it equal to 0, and then solve. All right. Any questions on our first example? Yes, sir.
You said f plus and f minus g and f times g are polynomials, correct?
Polynomial functions are a collection of terms. If we have a collection of terms that is written in decent order, which is the way we're supposed to present it, it's going to be from negative infinity to infinity, because we can choose any x value and still get a real answer. The only time that's not true here, and for these operations, is where we have rational functions. Remember, we can never divide by 0, so we got to figure out the x value to make the denominator 0 and exclude. All right. Any other questions, though? All right. The next thing we need to go over is finding the difference quotient, which actually has a formula. All right, so for the difference quotient, the formula is actually going to be f of x plus h minus f of x. This entire thing is being divided by h. All right, so with dealing with the difference quotient and dealing with functions itself, they got to give us the name of the functions. So when we're trying to find the difference quotient, we need to find f of x plus h, because they're going to have to give us f of x And then we're going to look to simplify if possible. All right? So our first example for the difference quotient, we'll do a couple of these. They give us f of x is equal to 2x squared minus 3x. And we're asked to find the difference quotient, which means we're going to have to plug everything into the appropriate place into this formula. We're given f of x already. That was given to us in the problem, 2x squared minus 3x. We need to find f of x plus h. Now remember, that while this can be, I guess it can be involved, the way that we work functions do not change. Remember, essentially, functions are substitution problems. Now, what we substitute will change depending on the problem itself. And the numbers we substitute can change as well, depending on the problem itself. But the way the functions work will not change. So when we're looking for f of x plus h, if we were looking for, let's say, f of 7, what we would have to do is replace every x in f of x with 7 and then simplify. So if we're looking for f of x plus h, it's the exact same rule. We're going to replace every x in f of x with x plus h this time, and then look to simplify. So f of x plus h will be 2 times x plus h squared minus 3 times x plus h. So essentially all we did was go in and replace every x in f of x and substituted x plus h in. I'm going to look to simplify. Remember, by definition, x plus h squared, when we square something, that means we're multiplying it times itself. So 2 times x plus h squared, that's really x plus h times x plus h, which is going to give me the polynomial x squared plus 2xh plus h squared. So simplifying, we go ahead and distribute that -3, multiplying both the x and the h inside the parentheses by -3, which is going to give me -3x minus 3h. And now we go ahead and distribute this 2 into the trinomial that we got from expanding x plus h squared. So this is going to give me 2x squared plus 4xh plus 2h squared minus 3x minus 3h. And this actually is f of x plus h because we have no more like terms to combine and we can't simplify it any further. Remember, we're asked to find the difference quotient. We have f of x plus h, or we should I say we just found f of x plus h. We're given f of x in the problem, so we have everything we need to plug into its appropriate place in the difference quotient. So now we can start working on that. This difference quotient, f of x plus h. No, I don't pick it up on the other page. Remember the difference quotient, f of x plus h minus f of x all over h. And notice that every time I'm working this out, I'm writing it out completely. The more you write it, the easier it is to remember. And eventually you get to a point where you've written it so many times, you don't have to try to remember it, you can't forget it. So we have f of x plus h. Remember that's that polynomial 2x squared plus 4xh plus 2h squared minus 3x minus 3h itself. I'm going to subtract f of x from it. Remember, the f of x was given to us. The following f of x, 2x squared minus 3x. And all of this is being divided by h. Now, notice that when I plugged in f of x, I subtracted it and put it inside the parentheses. Anytime we subtract a quantity, I do suggest that you put it inside of parentheses so that you don't forget or make the mistake of thinking that we're just putting negative 2x squared and then minus 3x. Remember, it's an understood -1 in front of this parentheses, which changes the signs. of both of them are every element inside the parentheses. So what was positive becomes negative, what was negative becomes positive. Or you can just look at it and remember that we're subtracting everything here. If we're doing this correctly, everything in f of x should cancel out. So essentially we have a negative 2x squared here and a positive 2x squared here. Those will cancel. We have a negative 3x and we're subtracting another negative 3x. Or if we subtract a negative 3x, that's essentially adding. So you can think of it like this. We have a positive 3x here, a negative 3x here. Those two terms will cancel as well. So what we're left with in our numerator, 4xh plus 2h squared minus 3h this is all still being divided by h. Every one of our terms in our numerator has at least one h in common. We can factor out an h from each of those terms in our numerator, which is going to leave me with a 4x plus 2h minus 3 inside my parentheses. All this is still being divided by h. And now that we factored out that h in my numerator, the h that we factored out and the h in the denominator can cancel. So our difference quotient, or f of x plus h minus f of x all over h, would be equal to 4x plus 2h minus 3. All right. Any questions on this example? Still working with the difference quotient. X squared minus 2x plus 4. Right. So remember the difference quotient, we need f of x plus h as well as f of x. We already given f of x, they have to give us that one problem. We need to find f of x plus h. F of x plus h, this means that we're going to replace every x in f of x with x plus h, which is a lot to say, not very much to do. It's essentially substitute. So f of x plus h will be 3 times x plus h squared minus 2 times x plus h plus 4. Just like before, x plus h squared is really x plus h times x plus h. So anytime we see x plus h squared, we're going to end up with the polynomial x squared plus 2xh plus h squared. That'll never really change. So if we end up with x plus h squared, it may help to go ahead and memorize this polynomial or this trinomial x squared plus 2xh plus h squared. We go ahead and distribute that negative 2 in front of the second parentheses or in front of our second x plus h. It's going to give me a negative 2x minus 2h. And we can bring down that positive 4 because we haven't done anything to that. Simplifying, we can go ahead and distribute this 3, multiply everything in this trinomial by 3. So f of x plus h ends up being 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 4. So now we can start working on that difference quotient. Once again, that's f of x plus h minus f of x all over h. So it's going to give me 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 4. This is f of x plus h. minus f of x, which is given to us in the problem. Remember, f of x was 3x squared minus 2x plus 4. All of this is divided by h. Now, I didn't do this in the last problem, but it may help. The only reason I typically skip this step is because it becomes a lot of tedious work. Once again, if you can remember that everything in here signs change, then you essentially can cancel out anything that's the same. All right, so like 3x squared, essentially we're taking 3x squared, subtracting 3x squared from it, so those will cancel. But there are some that would benefit from rewriting this. It's simply 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 4, and then simply going in and changing all these signs. What was positive becomes negative and vice versa. So this will become a negative 3x squared plus 2x minus 4. All of this still been divided by h. I just wanted to do that one at a time because for some, it may help to see the exact opposites and it helps them cancel. This way, and keep in mind, if we're doing this correctly, everything in f of x will cancel out. So when you're going through and combining your like terms, it may help to start at the end. So we have a negative 4, positive 4, those will cancel. Positive 2x, negative 2x, those will cancel. Negative 3x squared, positive 3x squared, those will cancel. All right. Now, it may be a little more writing and will take up a little more time, but if you know that you're the person that will benefit from that, do it every single time. All right. Now, what we're left with in our numerator, 6xh plus 3h squared minus 2h, and all of this is still being divided by h. So if you're doing this correctly, everything in f of x should cancel out, leaving us with terms in our numerator that have at least one h in common. So we can factor out that h in efforts to get it to cancel out with h in our denominator. So we factor out that h, we're left with 6x plus 3h minus 2 inside my parentheses. And remember, we're factoring out that h so you can cancel out with the h in our denominator in the difference quotient. So our answer ends up being 6x plus 3h minus 2. All right. Any questions on this example? All right, so the next thing we need to talk about is the composition of functions, functions inside of other functions. All right, so it looks like FOG are false, but it's read as F composed with G. This is how we compile. This is the composite function. By definition, F composed with G is F of G of X. All right, so remember that even with the composition of functions, technically the way that functions work has not changed. It's simply a different type of problem dealing with those functions. So essentially, we're still just substituting. Now, what we're substituting is going to change this problem. More specifically, we're given two functions, f and g, namely, and there are two types of problems that we can deal with the compositions of functions. We either take a number and run it through two functions, f and g, or we can substitute one function into the other, and we'll go over both. All right, so for our first example, if we're given f of x is equal to the square root of x plus 4, and g of x is equal to 2 divided by x. And the first thing we're asked to find is f composed with g of 2. Now, by definition, f composed with g of 2 means f of G of 2. So what we're really doing is taking 2 and running it through the machine of F, or excuse me, running it through the machine of G first, getting that answer, taking that answer, and then running it through F. All right, so we're going through 2 functions itself. The way I tell people to do this, if we have a composition of function and we're analyzing a number, work it from inside out. All right, so take note of that. If it's a number, we work inside out, or we're going to start this problem by finding G of 2 first. So G of 2 means we're going to replace every x in G of x with 2. Remember, G of x is just 2 over x, so G of 2 will be 2 over 2. Our G of 2 is equal to 1. All right, so now that we know that G of 2 is equal to 1, when we're trying to answer our question, which is f of G of 2, that's the same as f of 1. This is because G of 2 is 1. Can everybody see that? All right, so essentially what we need to find next is f of 1, which means we're going to replace every x in f of x with 1. Remember, f of x, the square root of x plus 4. So f of 1 will be the square root of 1 plus 4, or f of 1 will be equal to 5. All right, so this is going to be our final answer, just to be clear. F composed with G, oh, excuse me. I thought that square root, which is very important. It's not 5, it's the square root of 5. So F composed with G of 2 is equal to the square root of 5. All right, any questions on that first part?
How did you get F of 1?
You mean like, why are we looking for F of 1 here? All right, so remember, we're taking 2 and running it through these 2 machines. So when I said working from inside out, that means the inside part is what we're going to do first. So what we have to find first is the G of 2. You can see that G of 2 is equal to 1, right? Remember that we're looking for F of G of 2. So if G of 2 is 1, then F of G of 2 is really F of 1 because G of 2 is 1, which is very complicated to hear. It's a little simple if you just pay attention to it, like visually. Can you see that? So that's why we're looking for F of 1 to answer our original question, which is F composed with G of 2. All right, any other questions? All right. So if we can do that for F composed with G, we can also do this for F composed, or excuse me, G composed with F. Here we're going to be looking for G composed with F of 5. So G composed with F of 5 by definition is G of F of 5. All right, so the way that we're going to work this, exactly the same as the last one. Obviously, though, we're going to be running it through the same 2 machines and with a different number and in a different order. So just like before, we're going to work it from inside out. We're not going to look at this as one big hard problem. We're going to look at it as 3 small, easy problems. First problem, find F of 5. So F of 5 means we're going to replace every x in F of x with 5. But remember that F of x, the square root of x plus 4. So F of 5 will be the square root of 5 plus 4. We're going to be looking for the square root of 9, which we know is 3. So now that we know that F of 5 is equal to 3, G of F of 5 is really G of 3. And this is because F of 5 is 3, and that's what we just found. So now what we're looking for is G of 3, or we're going to replace every x in G of x with 3. So we want to remember the G of x is 2 over x. So G of 3 is simply 2 over 3. So to answer our original question, G composed with F of 5 is equal to 2/3. Any questions on this one? Still dealing with the composition functions. This time, we're going to be plugging a function into a function as opposed to running a number through two. So our first one, our next example, should I say, we're going to have f of x equal to the square root of x minus 1. Equal to 2x plus 5. And the first thing we're looking for is f composed with g. Now, by definition, this is f of g of x. Note that this time we don't have a number to run through these two machines. So we're going to be substituting a function inside of another function. If we don't have a number to run through two machines, like in the last example, when we work it inside out, if we're substituting a function into another function, we're going to work this one from outside in. By that, I mean, when we're looking for f of g of x, we're going to start by simply writing the outside function, in this case, f, exactly as we see it, except wherever we see x, we're going to leave an open parentheses because that's what we're going to make our substitution. So we have f of x, which is the square root of x minus 1. And we're not going to write x because this is where we're going to substitute g of x in. All right, so even though this is a little counterintuitive, essentially, no matter what type of problem we're having, we still are just substituting. And we're always going to substitute what's inside the parentheses. If it's a number, we replace every x and whatever the function is with that number. If it's an expression, we replace every x inside the outside function with that expression. So we're substituting g of x in. Here, we know g of x is 2x plus 5. So that's what goes inside the parentheses. So f of g of x is the square root of 2x plus 5 minus 1. Remember, it's an understood positive 1 in front of this parentheses. So essentially, we can drop it off and combine our like terms. So f of g of x ends up being the square root of 2x plus 5 minus 1, which gives me a positive 4. All right. Now the domain for this particular function in interval notation will be open bracket -2 to infinity, close parentheses. And I'll remind you guys of how we get this domain after we go over G composed with F. So we got G composed with F. Next we need to do, excuse me, we did F composed with G. Next we need to do G composed with F. So by definition, this is G of F of X. So this time we're going to be substituting f of x in for every x in g of x. So we're going to start with the outside function, g of x, which is 2x plus 5. We're going to write it exactly as we see it, except everywhere we see x, we're going to leave an open parentheses. So this time we're going to have 2 times open parentheses plus 5. Inside that parentheses is when we're going to make our substitution of f of x. Remember, f of x is the square root of x minus 1. So g composed of f of x ends up being 2 times the square root of x minus 1 plus 5. We don't have any like terms to combine. There is no simpler way of writing that. Now the domain for this function, the interval notation, ends up being open bracket 1 comma infinity close parentheses. And you want to remember that when it comes to these domains and these two particular functions, because we're dealing with radicals of the square root symbol, we can only take the square root of positive numbers and get a real answer and zero itself. So the way that we're getting this domain, for the first part, F composed with G, what we're taking is our radicand. Remember, that's just a fancy way of saying what's underneath that square root symbol. In this case, 2x plus 4. And we're going to set it greater than or equal to 0. So essentially, we're going to subtract 4 from both sides and divide by 2. This is how we ended up with x is greater than or equal to -2, and that's precisely our answer. End of notation. Every number greater than -2 and -2 itself will work. Exact same rationale here. For that square root of x minus 1, all we did was take the x minus 1. Our radicand was underneath our square root symbol. And for us, that need to be positive or 0. So we're going to make that greater than or equal to 0. And when we solve that, we end up with x is greater than or equal to positive 1. And that's our answer, end of notation. Any number greater than 1, and including 1 itself, will work. All right, any questions on this example? All right, so we have the composition of functions, the polynomial functions, the radical functions. We need to go over the rational functions, our fractions. And I can tell you now, these will be the ones that are the most involved. So we're given f of x, which is equal to 6 divided by x minus 3. And g of x is equal to 1 over x. First thing we're going to look for is f composed with g, which is f of g of x. Just like in the previous example, what we're doing is taking one expression or one function, plugging it into the other. So we're going to work these from outside in. So here I'm going to start with f of x, which is 6 over x minus 3. And instead of writing the x, I'm simply going to leave an open parentheses because this is where I'm going to make my substitution. And what we're substituting this time is what's on the inside. In this case, g of x. Remember, g of x is 1 over x. Now, before we simplify f composed with g of x, it actually will help us to start analyzing these rational functions in terms of the domains first. So remember, for f of x, at least the f of x given to us, we know x cannot be equal to 3. Because if x is 3, we're dividing by 0, and we know we can't do that. We also know that x cannot equal 0 for g of x. Because if x is 0, we're dividing by 0 once again, and we know that we cannot do that. Now, in terms of f composed with g of x, we have this expression. It still needs to be simplified. But we need to ask ourselves, what value will make this denominator, 1 over x minus 3, equal to 0, so we can exclude it? So we already know if x is 0, then the part that we substituted, the 1 over x, the g of x part, is going to give us an undefined answer. So we can't have that in our domain. So we know x cannot be equal to 0. And whatever value will make 1 over x equal to 3 in this case. Because if 1 over x is equal to 3, then we end up with 3 minus 3, or ultimately we end up with 0 on the bottom of our fraction again. And if we end up with 0 on the bottom, it cannot be defined. So we know we need to exclude 0 itself for f composed with g. We also need to figure out what will make 1 over x equal to 3, so we can exclude that. So 1 over x, we know, cannot be equal to 3. So we're solving this. The first thing I will do, multiply both sides by x, or we'll have 1 over x, just 1, because the x's will cancel. They're not equal to 3x. Let me get the x by itself. We have to divide both sides by 3. So the other value that x cannot be 1/3. So x can be any of these any value except for 0 and positive 1/3 for f composed of g of x. Now we'll write that in interval notation, but we still need to simplify this 6 over 1 over x minus 3. All right, so now we're just going to be focusing on that. That's 6 divided by 1 over x minus 3. Now, there's a couple of algebra techniques to simplify this. Me personally, anytime I have a fraction and we're adding or subtracting another fraction to it, instead of me thinking about common denominators, what I would do is turn 3 into a fraction by putting it over 1. And I would use a technique called the flying X. Now, the flying X technique is really the algorithm for adding and subtracting fractions, but it can take away all that thought about common denominators, because if you write the wrong common denominator, it's going to mess it up from that point forward. Now, the flying X is very similar to cross multiplication, except the cross multiplication is for proportions, or when a fraction equals a fraction, where the flying X is when we're adding or subtracting fractions. All right, so what we'll do is take the top left, multiply it by the bottom right. In this case, we have 1, because 1 times 1 is 1. Remember, this is for the addition or subtraction of fractions. So we're going to take the sign in the middle, be it a plus or a minus. In this case, it's a minus. I'm going to take the bottom left times the top right, or x times 3, which gives me 3x. And this is all over the bottom times the bottom, or in this case, x times 1, which is just x. All right. So now we have the complex fraction, 6 divided by the fraction 1 minus 3x over x. Now, technically, we can't divide a whole number by a fraction, especially when it's abstract like so. So what I would do, rewrite 6 as a fraction and divide it by that same fraction, 1 minus 3x over x. And I would do keep, change, flip. This is how we divide a fraction by a fraction. So we're going to keep the top fraction the same, change division to multiplication, and then we're going to flip the bottom fraction. This way it's not some complex fraction where we're dividing fraction by fraction. But what we're doing is taking 2 fractions and multiplying them, which is a lot simpler to do. So we're going to keep the top fraction the same, 6 over 1, change division to multiplication, and then we're going to flip bottom fraction. So what was 1 minus 3x over x is now x over 1 minus 3x. Now all we have to do is multiply the top and the bottom. So 6 times x is 6x. 1 times anything is the anything. So 1 times 1 minus 3x will be 1 minus 3x. And this is f composed with g. Now the domain for this particular function and the notation. Remember, we're excluding 2 values. Those values were 0 and 1/3. So we have 3 intervals. Values less than 0, values in between 0 and 1/3, and then values greater than 1/3. So our interval notation, it would be from negative infinity to 0 in parentheses, union 0, comma 1/3, also in parentheses to exclude both 0 and 1/3 itself, union 1/3, comma infinity in parentheses. So every value less than 0, every value in between 0 and 1/3, and every value greater than 1/3 will work. Now, I can tell you now, like I said, these compositions of functions, when we're dealing with rationals or fractions, that's going to be the most involved. If you can wrap your mind around these concepts, you probably won't have a problem. All right, now we've done f composed with g. Let's do g composed with f. By definition, G composed of F is G of F of X. We're working from outside in, starting with G first. Remember, G is 1 over X. We're going to write G exactly as we see it, except we're not going to write the X. We're just going to leave it open parentheses because this is where we're going to make our substitution. So we're going to substitute F of X, which is 6 over X minus 3. Now, before we simplify it, it's going to help us to look at this particular complex fraction and then ask ourselves what will make this undefined so we can exclude it in our domain. The only thing we really have to worry about is X minus 3 being equal to 0. So if X was equal to 3, this denominator is equal to 0. So we know that we can't include 3, or X cannot be equal to 3. And provided that X is equal to 3, there is no way for us to get 0 for the bottom of this complex fraction. Remember, this is 1 over the denominator. As long as X is equal to 3, we'll never get 0 for the bottom of our complex fraction because our numerator is non-zero. So all this to say that the only value we have to worry about excluding is 3. All right, so now we can simplify it. If you are well versed in reciprocals, remember if we have 1 over some fraction, to get rid of the fraction itself, we can just flip the bottom one or analyze it as a reciprocal, which would be X minus 3 over 6. By the way, this is G composed with F. But if you don't know this, you can do it like we did the last problem. By first making 1 into a fraction by putting it over 1, and then dividing by X, by 6 divided by X minus 3. And we can do the G change. Keep the top fraction the same, 1 over 1, changing division to multiplication, and then flipping the bottom fraction. So it was 6 over X minus 3 is now X minus 3 over 6. After that, we can multiply the top and the bottom, which is going to give us the exact same answer, X minus 3 over 6. Now, whether you change flip or just have a better understanding of reciprocals, doesn't make a difference to me. You're going to end up with the same answer either way. All right, so it's up to you to choose what route you take. But the domain is every value except for 3. So for this particular function, the domain is 2 intervals, negative infinity, positive 3 in parentheses, union 3 to infinity. Every value less than 3 will work. Every value greater than 3 will work. Like that. By that I mean rational functions and the composition of functions. I'm not going too fast. Anybody should comment? So the last example, given 2 functions f of x and g of x. This time f of x is equal to 5 over x plus 4. Where g of x is equal to 2 over x. So right off the bat, because we're dealing with rational functions, we know that for f of x, x cannot equal -4. Because if x is -4, we end up with -4 plus 4, or we end up with 0 on the bottom of our fraction. We can't divide by 0. We also know that x cannot equal 0 for g of x, because if x is 0, we're dividing by 0, which means we end up with undefined for g of x. All right, so first working with f composed with g. By definition, this is f of g of x. We're substituting a function in for a function, so with this one we're going to work from outside in. So we first start with f of x, which is 5, divided by x plus 4. And instead of writing an X, we're gonna leave it open parentheses because this is where we're gonna make our substitution. Substituting g of x in. G of x is 2 over x, so that's what we put inside our parentheses. When we simplify it, it will help us to look at this and see what values we need to exclude in the domain for f composed with g. We know that we have to exclude 0 because if x is 0, we end up with an undefined for the first part. But we know x cannot equal 0. And any value to make 2 over x equal to -4 will give me 0 in my complex fraction for my denominator. So what we need to do is take, now we're ourselves to the side here, 2 over x, and set that equal to -4 with the understanding that this is the value that we need to exclude. So to get that x out of the denominator, multiply both sides by x. This is going to give me 2 is equal to -x. Let me divide both sides by -4. Give the x by itself. The value that we must exclude is 2 divided by -4 are reduced. That's -1/2. But we know we have to exclude 0 and -1/2. All right, any questions on how we got those values? Because that's really going to be, I guess, the difficult part outside of simplifying and G-composed depth. All right, so remember, if we look at f of x, we said x cannot be equal to -4. This is because we had -4 here. Then we end up with -4 plus 4, or we end up dividing by 0, which we know we cannot do. But this complex fraction, or f composed with g of x, if we look at it as one big fraction, then 5 is my numerator. 2 over x plus 4 is my denominator. So we need to figure out what will make this denominator equal to 0. Just like before, if the first part, or what was typically x and f of x, is equal to -4, we end up with 0 on the bottom of our fraction. But because it's a complex fraction, or a composition of functions, should I say, we know that if whatever makes 2 over x equals to -4 is going to make it, or make the denominator equal to 0. So we need to figure out that x value to make that true. To do that, we take that 2 over x, set it equal to -4, the value that we know we cannot have, and then solve. All right, so that's where that -4 came from. Any other questions? All right, so now what we need to do is simplify this complex fraction, 5 divided by 2 over x plus 4. Me personally, I like to use that find x technique just because it takes away a lot of the thinking that we have to do. So the first thing I would do is make 4 into a fraction by putting it over 1. So now we have 5 divided by 2 over x plus 4 over 1. And now we can use that find x technique, which we can use anytime we're adding or subtracting fractions. So my numerator is still 5. Take the top left times the bottom right, or in this case, 2 times 1, which is 2. Remember, we use this for the addition and subtraction of fractions. So we're going to take the sign in the middle. This time, it's going to be a plus. Bottom left times top right, or in this case, x times 4, which gives me 4x. And this is all over the bottom times the bottom, or x times 1, which is equal to x. Remember that we call this a flying x technique because if you follow the procedure, it looks like we're making an x floating over the ground. All right, and once again, you hear me say this a bunch. Knowing how to do something important, knowing when to do it, more important. We only use the flying x technique if we're adding and subtracting fractions. So just like before, we have a complex fraction. We can take our numerator 5, turn that into a fraction by putting it over 1, still dividing it by 2 plus 4x over x. So that now we have a fraction divided by a fraction. And we can do our keep change flip. Keeping 5 over 1 the same, or our top fraction the same. Changing division to multiplication. And flipping my bottom fraction. So what was 2 plus 4x over x is now x over 2 plus 4x. And now we can just multiply the top and the bottom. So f composed with g will be equal to 5x over 2 plus 4x. This one want to remember that for the domain, we're going to have to exclude the values 0 and -1/2, which gives me 3 intervals. Values less than 0 are from negative infinity to 0 in parentheses, union. Oh, excuse me. The -1/2 should go first. Remember, less values go first. So negative infinity to -1/2 in parentheses, union -1/2 to 0, union 0 to infinity. So values less than -1/2, values in between -1/2 and 0, and values greater than 0 for. And for our last one, F, G composed of F. By definition, this is G of F of X. So this time we're going to be substituting F of X in for every X in G of X. We're working it from outside in, so we will start by writing G of X exactly as we see it, except we're going to leave an open parentheses for X's. Remember, G of X is 2 over X. So we're going to write 2 over an open parentheses. And inside that parentheses is where we're going to substitute F of X, which is 5 over X plus 4. Now, like I said before, we simplify. It will help to look at the unsimplified version to see what we need to exclude. As far as the big fraction, 2 over our denominator, once again, we don't have to worry about this fraction being equal to 0 because our numerator is 5. So 5 divided by anything except for 0 itself is not going to be 0. And 5 divided by 0 is undefined. So what we're really focused on is what will make X plus 4 equal to 0. And we're going to exclude that from our denominator. So X cannot be equal to -4 again. All right, so outside of that -4, every other value of X will work. And now we can focus on simplifying it. And for me, I would do the keep change flip. First, change 2 into a fraction by putting it over 1, divided by 5, divided by X plus 4. Keep 2 over 1 the same. I'll keep the top fraction, change division and multiplication, and flip my bottom fraction. So what was 5 over X plus 4 is now X plus 4 over 5. So G composed of F of X is just 2 times X plus 4 over 5. Now, this is technically the simplest way to write it because it's already factored. If you were to distribute that 2, I would have 2X plus 8 over 5. Algebraically, that's exactly the same, but it's not simple. In terms of domain, remember our domain is every value except for -4, which gives me 2 intervals. Negative infinity to -4 are all the values less than -4. Union -4 to infinity are every value greater than -4. Any questions on that last example? This goes over every type of problems you're going to see in 2.8. Remember, I posted the review Ch.2 already in the backboard. So if you have any questions, I'll be in my office this afternoon. Come by. I'll probably send you guys an email to let me know what time I'll be in the office. Assessment day. If you have questions, I do want to get an opportunity. If you have any questions, you guys.